We'll see the working of envelope detector. So we know envelope detector consists of a diode and a resistor and a capacitor, as it is given in the circuit diagram. Of course, when you see the output at this point, which is exactly the output at this point, so this point and this point are 100% same. So if I just measure the output at this point, it's exactly measuring the output voltage of a very simple circuit consisting of just one RD and CD. If I measure it over here, it's exactly the waveform at this point. So let us just find out if I measure the waveform at this point, what is the problem? Okay, let us apply a carrier signal. Okay, this is, we applied a amplitude modulated waveform with a carrier frequency of around 460 kilohertz. So we'll see what is the modulated waveform. I can see I have kept this in. The red one is the output waveform. Let us identify the reference of this one. There is a reference. You can see the demodulated version is above the reference by this much amplitude. You also identify the reference of this waveform also. You coincide that with the reference of this. Let us make their amplitudes both same. I can see it is 100% detecting the positive peak of the envelope. So there is no problem in demodulation. Of course, we are having a slight ripple over here. So the ripple in the demodulated waveform. So this ripple, the demodulated waveform, is because of the charging and discharging of the capacitor. So at what frequency we are having this ripple? This ripple is at the frequency of carrier frequency. So the problem at this point now is identify the grounds same. So whatever demodulated waveform we are getting is DC shifted and having some ripple. So ripple is at the frequency of carrier frequency. Now I'll just slightly improve this circuit diagram. So let me have the same circuit. Suppose if I just verify the waveform at this point, if I have this as my reference 0, so I'll have the output waveform demodulated version coming something like this. Of course, it is having some ripple at the frequency of carrier frequency. Now I'll just modify the same circuit diagram. So what I'll just do is, so this is the diode. I'll retain the same diode over resistor. This RD will be just split into two parts. Now this entire resistance is now RD. I'll going to simply retain this CD as it is. So this entire resistance, which was found out to be in your manual 220 kilo ohms, now I make this equal to 3.3 kilo ohms. So this I just retest as 220k, because 3.3 is negligible compared to 220k. I just make this 3.3 and 220k. Now I'll just make one slight modification. Now this is an ordinary envelope detector. We'll end up with the demodulated version. If this is the 0 reference point, so this is the demodulated waveform has got some DC shift, along with it has got some ripple. So the ripple amplitude is sufficient, and we are having the ripple frequency at the rate of the carrier frequency. We'll slightly modify this circuit. We'll just have the same OA79. We'll have same CD. I'll just split that RD into two resistors. So this is, let me call it as RD1 and RD double dash. So RD dash and RD double dash constitute the entire RD. So this now RD is equal to 3.3k plus 220k. So we are having this as 3.3 kilo ohms, this as 220k. So whereas suppose if I see the voltage this point, it's identical to the voltage at this point. So what I'll just do is, I'll just have a capacitor here. So this is a capacitor. So I have connected a capacitor, let me call it as CF. Now CF along with this 3.3k, of course you have to design the value of CF such that the cutoff frequency of, now will this constitute a low pass filter? You can see this RD dash and CF is now constituting a low pass filter. So this is a low pass filter now. Now when you pass this signal through this low pass filter, so because this ripple is at a frequency of 450 kilohertz, which will be the carrier frequency, we'll certainly have at this point, this is the output of the low pass filter, we'll certainly have again an elevated waveform. The demodulated waveform is still having some DC shift, but you can certainly see there is a reduction in the amplitude of the ripple. So you can see this amplitude, which was more before the filter, has been reduced to just bit less after the filter. Now this is that when I just split that RD into two resistors, one part of RD and CF is now constituting the low pass filter. Now the cutoff frequency of that low pass filter should be such that this is 2 pi RD dash into CF. So this should be sufficient enough to pass the modulating signal. Suppose if your modulating signal is 1 kilohertz, you keep the cutoff frequency of this filter so that it is just passing 1 kilohertz, so that it will block the ripple. So at this point I'm still having the DC shifted waveform. I'll put one more capacitor here. So I'll just put a capacitor which will block the DC. So if I, okay, this is one more resistor which is used as a load resistor. So this you can have it as 100k. This you just block it for this capacitor used to block the, you can have a 0.1 microfarad capacitor. Now what is the difference at this point? Now at this point I'm going to have the waveform. Now you can see it is exactly the same waveform as it is at this point, but only difference is that it will not have any DC shift. So I'll still have the same output waveform which is there before the 0.1 microfarad. You can see there is a slight amount of ripple, but the difference between this point and this point is that at this point I'm going to have a pure AC signal without any DC shift. So we can just see at different points. At this point I'm going to have the demodulated waveform with DC shift along with large ripple. At this point I'm going to have the DC shifted with reduced ripple. At this point it's a perfect demodulated waveform without any DC shift and without that much ripple. That we can see it on the circuit also. So you can see over here now. So this is that's the modulating signal. So let me first see at this point. So you can see, since I have identified both the grounds, so I have just identified both the grounds over here. Let me just coincide to the, I have identified both the grounds. You can see now the output is identify both the grounds. You can see at this point, this is just before filtering, before passing it to the low pass filter. You can see the amplitude of the, you can identify, first what you can do is you can identify the reference of both the signals, release both the references. Now you can see, let us have both of them in same voltage division. You can see it is just before filtering, before passing it to the low pass filter. You can see the amplitude, you are having some ripple. You can see the ripple over here. So this is what is the ripple we are having. You can see on CRO, okay, you can see the ripple amplitude. So this is the ripple amplitude of the output waveform. Now we can certainly reduce that ripple. I identify the references so that you can make out the DC shift of. Now let me just only see the output waveform, so let us not see the input, so that you can make out the effect of your low pass filter. Now this is before filtering. You can see what happens if I just pass it through after the filter. Let me just compare both the waveforms on CRO. So one point happens to be before the filter, so this is before filtering, this is after filtering. You can see the difference between both of them. You can see the amount of ripple reduction in the amplitude of the ripple. The above one is, the above one is not having that much ripple. You can clearly make out that difference if I just increase this. Of course you can clearly make out over here. It may not be so clear on your screen, but you can clearly make out on CRO there is a lot of amplitude in the before filtering and after filtering. After filtering it is going to have a bit more smoother waveform. The above one is after filtering. Now next you can still see there is some DC shift. So even before and after filtering we are still having the DC shift. So you can just identify the grounds of both of them, you coincide them, you can still both are there having some DC shift. So since they are in, you can see both are there coinciding. But you can see just after that, now I'll just verify the waveform at this point, the waveform before I just block the DC and after I block the DC. So what we saw was the waveform before I filter it out and with the waveform after filtering. So we can still able to see there is a reduction in the ripple amplitude at this point compared to the point just before the filtering. Now I'll just verify before I block the DC and after I block the DC. So this is the waveform before I block the DC. You can see both of them are there in DC position. You can see this is also there in DC, this is also there in DC. So whatever that I'm showing now is the input waveform before I block the DC. You can see it has got this much amount of DC shift. You can see now. So this is the amount of DC shift. Now I'll just see the other waveform. The below one is also there in DC. Even though I just put this in DC position, you can see at the output, since it is not having any DC component, so the below one is a DC blocked demodulated waveform. So compared to the above one, which has got some DC component, the below one is pure AC signal. That's what is demodulated waveform. That means at this point I'm having a pure demodulated waveform without any ripple. You can see at this point I'm having the waveform which is having a pure AC signal with small amount of ripple. So there is slight amount of ripple is there, but you can see it's a pure AC signal. So this is about the working of this envelope detector. So coming to the conduction of this X-ment, so what we'll do is we'll just measure the output voltage. So we can start with the modulation index which is slightly less. So you can start with, I can measure the modulation index for each and every variation. So you can identify what is VM max and VM min. So that's what will give the modulation. Vmax and Vmin will going to give the modulation index. For each and every variation you can just note the output amplitude. So what I'll just do is I'll increase the amplitude of the modulating signal, which will increase the modulation index. So you change the modulating amplitude, you can see this has changed. The output will also increase. So we're going to plot the first one. We're going to increase VM, the modulating amplitude. We're going to see how does the percentage of your modulation, what we'll see is we will increase the percentage modulation, we will see what is the variation in the V0. So as I increase the modulation index, your output voltage almost increases linearly. You can see if I keep on increasing the amplitude of the modulating signal, which certainly increases the modulation index, is also increasing the output amplitude. You can continue this increase of the modulation index unless your output is facing that negative peak clipping. You can see that negative peak clipping. If I further increase it, you can see now you can see at the bottom you are having a flat waveform. So this variation is not a sinusoidal one. So the modulation index at which this happens is known as Mmax. So even we are not having any problem in the modulation, we are going to have a problem in the demodulation, which we call it as Mmax. So you can identify what are the modulation index at the input, where exactly you are going to get a flat waveform at the bottom. Next, after that, we'll keep the modulation index around 50%. We start increasing the frequency of the modulating signal. So as we start increasing the frequency of the modulating signal, you can see at the demodulation, now we'll just keep on increasing the frequency. Since the frequency is just 200 Hertz, we're not having any problem. Let us go for a frequency slightly more than that now. Now you can see I'm just increasing. There is no problem while rising. You can see it has started deviating from here. So you can just coincide that too. You can see while decreasing, it has got a exponential decay rather than a sinusoidal variation. If I further increase the frequency, it further deviates. You can see it is further deviating. So we have exceeded that modulating frequency where we are not giving a faithful demodulation. So we can find what is FM max. It's the frequency at which this exponential decay begins. So this is already started. Let me slightly reduce the modulating frequency. I'm reducing. So this is what is. So if I go slightly beyond this, the modulation index is, sorry, the demodulated waveform is losing the shape. It's not becoming a sinusoidal variation, it is becoming exponential. So we can take this as the FM max. FM max happens to be here around, so this is 2 kilohertz and this is 480 hertz. If I go beyond this one, the demodulated waveform is going to lose the shape, so it is becoming exponential while coming down. So 480 hertz happens to be the FM max. So by this way we can find what is FM max and Mmax.